All right, we'll give it maybe 2 minutes to allow some more folks to sign in, and then we'll get started. All righty. Welcome everybody to the virtual speaker event with Wenatchee River Institute. I'm Rachel Bishop. I'm the Community Programs Manager. And just a real quick, in the comments section, that's a great place for you all to write in questions at any time throughout the presentation. And at the end, I will make sure all questions are asked. And so before I introduce our speaker tonight, just wanted to give folks a little information about who we are. We're Wenatchee River Institute, and we're an environmental learning center in Leavenworth. And our mission is to connect people, communities, and the natural world. And as you might imagine, our programming looks a little different right now. We're doing a lot of our community programs like this virtually, and we were going to experiment with some in-person programs, but that may not be happening with the new guidelines from our governor. And for our youth programs, we have been having some in-person small group camps with kindergarten through 5th graders, all masked, all outside and social distanced, and still having lots of fun and connecting with the natural world. And we're also offering virtual education for elementary teachers and classrooms in North Central Washington. So we have different videos to offer and at-home activities, as well as virtual field trips at our campus in Leavenworth. And so if you know of any teachers who are looking for extra help in the classroom, please reach out to us and let us know, and we'll connect with them. And just a little bit about a couple upcoming programs folks might be interested in. Starting next Tuesday, November 24th, we have a 5-class series, which is learning the language of the indigenous folks of Leavenworth. So that's learning the language of the Wenatchee people, and they're also known as the Pisquosa. And the language you will be learning is the Inhamchin language. And it's 5 Tuesdays, 1 hour each, basic introduction of the language, and also learning a little bit of cultural history as well. And there's only 3 spots left in that class. So if you're interested, head to our website and sign up quick before they disappear. And we also have 2 other virtual speaker events coming up in December. So December 10th, we have a speaker from Trout Unlimited talking about a local project on the Icicle River. It's called the Icicle Boulder Project. And they were working this summer and fall to open up more of the Icicle River to steelhead and bull trout, opening up more spawning habitat. So on December 10th, you can tune in to hear more about the status of that project and how it went and what their goals are. And then also on December 14th, we have a woman named Angie Lane from the Department of Natural Resources she will be presenting virtually about Washington's 2020 fire season. So she's going to be talking a lot about the Labor Day event in Washington, and just also about how COVID affected preparedness of the fire folks. So as a recommendation for folks who are looking to learn more about the programs we have, the best way to find out about upcoming programs is by signing up for our e-newsletter. And that goes out twice a month. And you can sign up for that on our website, which is wenatcheeriverinstitute.org. And you can also follow us on social media if that's something that you do, or you can just keep an eye on our calendar on our website. All right, so I am going to introduce our speaker for tonight. So tonight we have Seth Moran, and Seth's professional career has been focused on the study of active volcanoes and volcano seismology. After graduating with a geology degree from Oberlin College in 1988, he earned an MS in 1992 and PhD in 1997 in geophysics from the University of Washington. In 1997, Seth was hired by the U.S. Geological Survey to work as a research seismologist at the Alaska Volcano Observatory in Anchorage. In 2003, he transferred to the Cascades Volcano Observatory in Vancouver, Washington, to work as the principal USGS seismologist, responsible for studying and monitoring volcanoes in the Cascade Range. He played a lead role in the response to the 2004 through 2008 eruption of Mount St. Helens. From 2015 to 2020, he served as the scientist in charge at the Cascade Volcano Observatory. Please welcome Seth.
Well, good evening, everybody. And let me get my presentation going here. And welcome from the southwestern corner of Washington. I'm down here in Vancouver, Washington. And like Rachel said, I work for the Cascades Volcano Observatory. For those of you who have never heard of the U.S. Geological Survey, it's, if people have run into that organization, typically you associate us with things like topography maps, or maybe also stream gauge work. There's also USGS work that is involved in earthquakes, in natural hazards, and in energy mineral resources. We're a bureau within the Department of Interior, and we share that with the National Park Service, with the Fish and Wildlife Service, with the Bureau of Land Management, and the USGS is looked to as the scientific arm of the Department of Interior. So there's a lot of different places that USGS work comes to bear in terms of helping the nation manage its resources. So my particular part of the world is in volcano hazards, and the folks at the Cascades Volcano Observatory, this is a picture of us back in happier days when we could all be elbow to elbow without worrying about catching something nasty. There's about 80 to 85 people that are working at the observatory. And the observatory was born out of the May 18, 1980 eruption of Mount St. Helens. Before that time, there was no USGS presence, no Cascades Volcano Observatory. When the eruption happened, it was so huge, and the magnitude of it in terms of the changes to the landscape, the deposits it had produced, the kind of precedents that it set in the volcanology world, that alone was enough to make it clear that there was decades worth of science to be done at Mount St. Helens just to fully understand what happened, let alone to continue monitoring the volcano because it was still erupting. But also there were lessons to be learned in terms of how to better help society deal with eruptions. The response in 1980 was okay. There were some parts that went remarkably well. There were other parts that didn't go as well, one of which was there wasn't a lot of information that went to people who were quote unquote downwinders. A lot of ash from the 1980 eruption went shooting across the state of Washington and dumped a lot of ash in places like Yakima. And the communities there hadn't really been prepared by the folks who were working on St. Helens to deal with the ash. And so one of the learnings from that is there's better things that should be done in terms of community preparedness. So those are the real reasons why CVO was formed. And today we're not just about Mount St. Helens, we're about all the volcanoes in the Cascade Range. CVO is one of 5 volcano observatories in the United States, in the USGS. We're all organized under one organizational umbrella. We collectively divvy up the 160 plus active volcanoes in the United States. And by active, what we mean is have the potential to erupt again. Not obviously, they're not erupting right now, at least not all of them. There's a few that are. But active means they're still alive and there's still a potential for them to erupt again. And so the other observatories include the California Volcano Observatory. There's also the Yellowstone Volcano Observatory. There's the Alaska Volcano Observatory, where I used to work. And then our oldest observatory is the Hawaii Volcano Observatory that was born back in 1912. So the importance of all of us being organized together comes out when one of the observatories has a large eruption that occurs under its feet. And that happened in Hawaii in 2018. And some of you may remember there was some spectacular news coverage for a couple weeks about a major lava flow eruption that occurred on the lower East Rift Zone out of the Kilauea volcano. And this is what that looked like. There was a very persistent fissure with a fire fountain coming out of it and a lava flow that went through a lot of neighborhoods and destroyed all told 700 plus homes. So this was a 3-month-long event where a lot of help was needed by HVO, because HVO was overwhelmed by all the things that needed to be done in response to this eruption. And so all told, about half of the folks that work in the other observatories came out to Hawaii for periods of a week or a couple weeks to help out in different ways. And that's also a valuable way for all of us to gain experience in responding to volcanoes. And I was out here at Kilauea for a couple of stints to help out as well. So for CVO, here we are down here in the greater Portland metropolitan area, just across the river from Portland. And these triangles here show the locations of all the places, all the volcanoes in the Western US. The easternmost volcanic center that's considered still active in the sense of it could erupt again is just a little ways south of Albuquerque, New Mexico. Pretty much every state in the Western US except for Montana has at least one volcano in it. And the turf for CVO is Washington, Oregon, and Idaho. And that includes famous volcanoes like Mount St. Helens, as well as Crater Lake down in Oregon, and then less famous volcanoes like Glacier Peak, which is the closest volcano to the Leavenworth-Wenatchee area. And it's a volcano that not many people know about. It's tucked away in the Glacier Peak wilderness. Nobody lives close to it. It's very hard to access it. It's a very rugged topography. And it's hard to see because it's surrounded by pretty high ridges. So it's not one that what people know about, but next to Mount St. Helens, it turns out to be the most explosive volcano in the Cascade Range. And so it's worth knowing about. And then there's really not well-known volcanoes like diamond craters out here down in southeastern Oregon. The Cascade Range has a number of interesting features to it. One of which is you'll notice that these triangles, there's not a great density of them in Washington, particularly in the northern half of Washington, but getting down into Oregon, there's a lot more of these triangles. And there's a couple spots actually down there where you can stand and have what volcanologists anyway would consider to be an outstanding day, which is a 10 volcano day. Here is that vantage point looking west towards the Cascade Range. And there are 10 named volcanic centers that you can see from one place. And actually from here, you can see more than that. There's a volcano called Newberry off to the side over here. And also Mount Adams, I'm pretty sure I can make it out over there. So this is actually more like a dozen volcano day. Pretty outstanding. There's very few places in the world, it turns out, where you can see this many volcanic edifices, cones, in one place. And so there's some interesting questions to ask about why is that the case in Oregon? And that's one of the things that a lot of people have been doing research on over the last several decades. Another thing that's interesting about the Cascades is, this actually isn't really the Cascades, it's in the western side of the Cascades. This is the Portland area, again, where I live. I'm actually talking to you from just right here, just a little ways above the Camas. And CVO is located right here. And all these red dots correspond to locations where magma's come out of the ground over the last several million years. This is a volcanic field that's known as the boring lava field. And turns out that there are eruptions here about every 15,000 years, with the most recent one being 57,000 years ago. So on a human timescale, this is not anything that we need to worry about. The last time this erupted, there actually weren't people here at all. And, but it's something that could happen. And there's some interesting questions about why this is going on, because in terms of our understanding for where volcanoes, or for why volcanoes exist where they do, the Cascade Range, there's a good understanding for why volcanoes are clustered along the mountain range. But these volcanoes are not on the range. They're too far, they're too close to the ocean. And there's not many places in the world where you get volcanoes popping up sort of between the volcanic arc and the ocean. And so that's another thing that's just kind of mysterious and interesting about the Cascade Range. And I should point out that from our office, when we're there, not in pandemic times, we can see a volcano. And this is Green Mountain, which is CVO's local volcano. You can see it's got a very nice cinder cone. So this may be one of the reasons why in the Pacific Northwest, there's some really outstanding beers that are named after volcanoes. You've got Black Butte Porter, which is my personal favorite. A lot of these are named after Oregon beers, Oregon volcanoes, which may reflect well, I don't know, it could reflect a couple things. One, maybe Oregon makes better beer, but another is maybe there's more volcanic centers in Oregon. The most famous of all these probably is Rainier beer, and I won't make any statements about whether that's a good one or not. So here we go, zooming in now into Washington and Oregon, and this is the real sort of focus of our group. And in Washington and Oregon, there are 25 of these triangles, volcanic centers, which have erupted in the last 12,000 years. And the significance of 12,000 years is that's since the last ice age. And the last ice age came through here and really eroded a lot of evidence of volcanic eruptions that happened before the ice age and also during it. And so particularly in from sort of Olympia north, that's the tongue, the extent of the glaciers from the last ice age. And a lot of volcanic deposits were erased by that ice age. So we have a pretty good sense of what the record is from 12,000 years to the present. And there are colors here for the different volcanic centers. And the colors correspond to what we call a threat level. And what that means is that we've gone through, the USGS has gone through all 160 volcanic centers in the United States and ranked them using two ways of ranking. The first is to look at the hazard. What has the volcano done? What can it do? So how frequently has it erupted? How explosively has it erupted? And then also combining that with the exposure of society to those hazards. So a place like Glacier Peak, surrounded by wilderness, there's not a lot of exposure, particularly relative to a volcano like Mount Rainier, where there are over 90,000 people that live in hazard zones there. So you take those two things, you take the hazard and the exposure, you bring them together, and then that score, you rank all 160 in the United States. And it turns out you can group things in terms of different degrees of threat level. And so these red triangles correspond to the highest threat categories. And in the United States, there are 18 very high threat volcanoes, and 8 of those are in Washington and Oregon. Amongst the other 10 include places like Kilauea in Hawaii. And there's a few in Alaska. But almost half of them are in Washington and Oregon. And in Washington includes Mount Baker, Glacier Peak, Mount Rainier, Mount St. Helens. And in Oregon, it's Mount Hood, Three Sisters, Newberry, which is just south of Bend, and then Crater Lake. And then also there's one volcano, Mount Adams, that's considered to be high threat, just the next tick down. So really there's 9 here that we focus on. Most of our energy is focused on because these are the ones where the hazard is highest and exposure to society, to those hazards is highest. If you add up all the eruptions that have happened in the Cascades that we know about over the last number of thousands of years, you come up with an average of about 2 eruptions per century. And in the 20th century, there was the Mount St. Helens 1980-86 eruption. There was also an eruption of Mount Lassen, which is just off of here. It's considered a Cascade volcano. That was in 1914 and 1917. So there were 2 there. In the 19th century, Mount St. Helens was active between about 1800 and 1857. So you could call that kind of 2 eruptions because it wasn't continuously active. There were breaks in there. And then in the 18th century, Mount Hood erupted in 1781 to 1793. So a lot of these eruptions are also multiple year-long eruptions. The 1980 eruption at Mount St. Helens lasted 6 years. The 1781 eruption at Mount Hood lasted for 12 years. And so one thing we say is that on average, 10% of the time, a Cascade volcano is going to be erupting, probably Mount St. Helens. And if you live your entire life in the Pacific Northwest, you should expect at least 1, if not 2 eruptions in your lifetime. Likely not going to be huge deals like Mount St. Helens was in 1980, but they'll still be very important events, memorable events. So our job at CVO, to put it bluntly, is to help society live safely with volcanoes. We have volcanoes in our midst. It's part of the physiography of the Pacific Northwest. It's one of the things that makes it such a cool place to live. We've got spectacular mountains that are a result of tectonic processes that produce earthquakes that are large and have a lot of hazards with them, also produce volcanoes. And it's our belief that society can live with volcanoes safely. And it's our job to help society understand what the hazards are, what kinds of things can happen, and what to do about them. So this is a cartoon that shows in sort of a simple form what the hazards are, what volcanoes can do. So this is partly this is a cross section, or think of it like a slice out of a cake. This shows a body of magma down below that's feeding the volcanic vent at the surface. And then depending on the kind of magma that comes out, you can get a lava flow, like what happened in Kilauea in 2018. Or if it's more explosive, you'll get bombs coming out, or you'll get ash going up into the air and creating tephra down below. You may also get what are called pyroclastic flows. These are density currents or dense flows of hot gas and ash that can flow long distances. Very hot. If you're caught in them, people who get caught in them, this is one of the ways you die pretty quickly in volcanic settings. And they can be very, very hazardous. Also, there are these things that are called lahars, or debris flows or mud flows. These can be created in volcanoes by having hot rocks land on ice and snow, which is a particular thing for the Cascades, where all of our volcanoes are snow covered at least half of the year. You can also get this in other ways, one of which is a landslide that can happen. And then sort of other less common kinds of things. So this is a picture of the most common kinds of hazards that we think about when a volcano erupts. And this is what our job is in terms of helping people live with volcanoes, is to understand what these are and what particular array of hazards you should expect from particular volcanoes, because not every volcano is the same. And would not expect to see, for example, a Kilauea style lava flow coming out of Glacier Peak. So wouldn't be thinking about that so much. We would be thinking about explosions. So the way that we do our job is through 3 functions. We work in research, we work in monitoring, we work in community preparedness. And I'll just walk through each of these to give you a sense of how each of these, of how we do each of these. So first, focusing on our research. One of the very important things that geologists do in our observatory is to come up with eruption histories. And that gives us a sense of the frequency as well as the style of eruptions that have happened in the past. And in geology, there's a key tenet, which is that the past is the guide to the future. And in volcanoes, that's particularly the case, that volcanoes tend to do what they've already done. And so we can say things like, Glacier Peak, geologists have gone out there, they don't see lava tubes. They don't see large lava flow fields like you would see in Kilauea. Instead, they see large ashfall. And so that's part of the playbook that we have to work with the next time Glacier Peak wakes up. So this diagram here, it's one of my favorite diagrams that CVO has ever produced, shows for all the Cascade volcanoes going back 4,000 years. So on the lower right-hand corner is time scale, and this is the present and going back 4,000 years. These volcano icons correspond to a time when geologists are pretty certain magma came out of the ground at this volcano. And so the brilliant thing about this is that you can go and with your eye, and I'm guessing some of you may have already done this, count up the icons and come up with your own answer for what's the most frequently active volcano in the Cascades. And if you do that, here's the answer that comes out of it. Mount St. Helens, #1. Glacier Peak, #2. And then you go down to California for Shasta, Medicine Lake, and then back up to Washington for Mount Rainier, #5. And so this, this gets at the question of what's the most likely volcano to erupt next. And using the geologic, the tenet that the past is the guide to the future, Mount St. Helens has been the most frequently active in the past. It's most likely to erupt again in the future. That's our belief, and has proven out. This graphic was done in 2000, and in several years after 2000, there was several summers of very careful geologic work at Mount Rainier that looked at the question of, are there deposits that were missed by past geologists that might tell us more about the eruption history? And this next graphic, you'll see that Mount Rainier has a lot more volcano icons. This is just 8 years later. And now Mount Rainier is #2. Mount St. Helens is #1. So this fairly careful geologic research upped our understanding for the relative frequency of eruptions at Mount Rainier, particularly between 2,000 and 3,000 years ago. That would have been a very interesting time to be around here because it was erupting about every century, just like Mount St. Helens was. The last eruption there was 1,000 years ago, so we don't necessarily, we might be in a pause right now, but we've not experienced one in a while. But Glacier Peak is #3. Now, one of the things about Glacier Peak is that it's rugged. For those of you who've been out there, you know how hard it is to get out there. And this is an area right now of active geologic research. And I'm just going to take you out there for a little bit. This is a picture that was taken a couple miles to the northeast from Glacier Peak summit. And what's being shown here is obviously a hillside, and there's a lot of dirt that's covering rocks here. This dirt turns out to be ash. And it's got layer names here, the G tephra, the B tephra. Tephra is Italian word for that means ash. And there's a geologist for scale. So that's about 6 feet. And this is tens of feet of ash that fell. This is from an eruption that happened 13,500 years ago. That was roughly 5 times the size of 1980 Mount St. Helens, and would for sure have dropped ash in the Wenatchee area. And if it were to happen today, even though this is in the middle of wilderness, the ashfall would have caused a big problem for people in the downwind side of things. And so it would matter a lot which way the wind's blowing, which is the same thing as when there's wildfires out there. It matters a lot whether you breathe it or not, depending on which way the winds blow. And so that is certainly a hazard to be concerned with. So the work that's been done on at Glacier Peak so far has unearthed this time scale, this perspective, which is this big eruption 13,500 years ago. And then you go a while, almost 10,000 years, to an eruption 6,000 years ago, and then 3,000, 2,000, 1,000, and maybe closer to the present. And one of the things that we don't know is that, that these most recent eruptions are the easiest ones to know about because their deposits have not been as eroded as others. And so it's easier to find. And it's possible that there's eruptions that have happened in between these gaps that we just haven't found the deposits for because they're under the ice, or it's just been really hard to find those key locations that have the evidence that geologists need to be able to determine the full eruption history. So this is work that's ongoing. It's reasonable to expect that in a decade, there might be a few more of these eruption icons on the Glacier Peak timeframe. One thing we do know about is that if you ignore this 13,500 year ago event, the rest of the eruptions that have happened at Glacier Peak have been explosive, but they've been smaller than Mount St. Helens 1980, on the order of 10 to 20% the size of 1980. And so that's something that is at least a little bit reassuring. So that's one form of geologic research. One of the results of geologic research is putting together hazard maps, which is a way of depicting our understanding of what's happened at the volcano and what could happen in the future that would be problematic for people. So this map here shows, it's a simplified hazard map in the sense that it's showing zones. It's not showing specific scenarios or specific products. And so this kind of, I don't know, darkish pink color is what we would call the near field zone. This is a place where the ballistics would be an issue. This is a place where pyroclastic flows would be an issue. This would be a place where things could happen very fast, within tens of minutes. And if you were there, there'd be little chance of anybody coming to rescue you for sure. And also you'd be in danger. So this is the kind of thing where if Glacier Peak were to wake up, there might be a closure zone that might reflect this kind of a boundary. And then outside of that, there are these ribbons that have colors that go from red down to orange down to yellow. And these colors are intended to signify likelihood, that it's more likely that there's going to be a specific hazard. In this case, it's lahars, these volcanic mud flows, happening here than down, say, near concrete. And same thing for Darrington. Now, for folks in the Wenatchee-Leavenworth area, Lahar hazards aren't really a thing to be concerned about because the Cascade crest is diverting all of the water, all of the drainages from Glacier Peak. They all flow out towards the Puget Sound. So this is not something that if Glacier Peak were to wake up and we were to come out and have community meetings in, say, Kashmir, we wouldn't be talking to you about lahars. We'd be talking to you about ashfall. That would be the primary hazard that would be of concern for Glacier Peak. And that's not represented on this hazard map. This hazard map is much more focused on ground-based flows. So speaking of ashfall, what are the chances that there might be measurable ashfall in Wenatchee from Glacier Peak? And that's a question that could be asked just like, somebody deciding to move up there and they've heard about this potentially huge eruption and maybe they're a little worried about what the chances of ashfall might be for them moving there. So this map here shows a probability distribution that's based on a model that's been run about 1,000 times, taking historic wind field data from the National Weather Service for 1,000 different days. So randomize, grab 1,000 days of wind field data. Sometimes the winds are blowing to the west, sometimes they're blowing to the east. And then the model puts ash up into the air of a certain volume and then tracks where the ash goes and where it lands. And what these lines here, or these contours are likelihoods of trace amount of ash, more than trace amount of ash falling. It's basically measurable ash. So this outer contour is 1%, then we go 5%, and then 10%, and then 30%. And here's this circle here, which corresponds roughly, I might have moved it a little bit too far to the east, roughly that's the location of Wenatchee. And so it's right in this kind of between 10 and 30% chance. So this is what this is showing here is if there's an eruption, then the winds would be favorably oriented to bring ash into the Wenatchee area, something like 15, 20% of the time. But it's a two-step thing. If there's an eruption, and then also what are the winds doing? So the first thing to understand is what are the chances of an eruption? Just from right on today. So the most likely eruption I mentioned before is not this big huge one. It's a small, what we call a dome collapse, or a lava dome that builds up. Sort of lava is sticky, so it doesn't flow. Instead, it builds up into this bulgy like dome, and then parts of it collapse because it's building on unstable, steep-sided volcanic slopes. And so we have a sense of the volume of what that might be. That goes into this model. And then we know that there have been 4 eruptions in the last 10,000 years. So that's one every 2,500 years. So that's one very important part in the probability of somebody asking the question, if I move to Wenatchee, what are the chances? The big thing is that one in 2,500 years is not great odds. So then you take that, and also here's the model. You model the ashfall using wind field data for 1,000 random days, and the answer is, so here's the dot: 50% chance of 1 millimeter of ash, which is a trace amount, about 1/4 of an inch, if there's an eruption. So you take the 15% chance, multiply it by 1 in 2,500 years, and here's what you get. It's a 1 in 16,667 annual chance, or a 1 in a little over 6 million daily chance of a measurable amount of ashfall falling in Wenatchee from Glacier Peak. And so to put that in perspective, the Powerball odds, 1 in 292 million. Every time there's a Powerball, that's the odds of you getting it. So the daily chance of having Glacier Peak ashfall, it's actually more likely that you would get ash from Glacier Peak than winning the Powerball. However, chance of getting into a car accident, daily chance, way, way, way higher. So in terms of things to be concerned about, or ways to live your life, this probably says don't buy Powerball tickets, but also don't worry about Glacier Peak. First, worry about driving and driving safely. And so it's that kind of thing that maybe helps people put things a little bit into perspective about that. But the biggest thing is that you don't need to worry about it until Glacier Peak erupts. And the likelihood of that happening is not that large. Probably every 1,000 years or every 500 years. And then if it happens, then that's where we come in. Just to give a sense of what ashfall looks like, it has happened in the Pacific Northwest with Mount St. Helens. It happened for sure going into Wenatchee. It also, there was a weird day where the winds were blowing to the west, not on May 18th, but in June, there was an eruption at Mount St. Helens, and ashfall fell in kind of the I-5 corridor. So here's Mount St. Helens, and it came down to the Portland metropolitan area, went up to Tacoma, actually went all the way out to the coast, which was really weird. And what that looked like in Portland, this is the 405 going down towards Portland State, and it looked like fog, except that it's just kind of in the air. And for those of you who have driven on Forest Service roads or dirt roads, you don't want to get too close to cars in front of you because you eat their dust. And this is what eating dust looks like for ash. Ash just stays in the air for forever because it's a lot lighter than the stuff that you get on Forest Service roads. And so visibility can be a huge, huge problem. Also, ash gets into motors and breaks them. And so there's a lot of concerns about ashfall, and a lot of things that need to be understood about how you mitigate ash once it's fallen. And that'd be one of the things that we'd be coming out to help people understand where Glacier Peak to wake up. Just a quick touch on Lahars. This is a long-traveled, along with ashfall, it's another one hazard that impacts people away from the volcano. And I mentioned before, but this picture really shows it, that one really great way to get a Lahar is to have some kind of hot eruption. That shows Mount St. Helens. 1982, there was a big explosive eruption that put a lot of hot rock in the crater, melted snow, and then this black deposits here are Lahar deposits that came out right in response to that and went downstream a decent distance. And these pictures down here show Lahars from 1980, quite a bit bigger. I'm just going to show you a quick video. This is a way small Lahar debris flow captured in Mount Rainier in 2015 by some tourists. And you may be able to hear the audio, but you can certainly see this flow coming, and there's a lot of debris on top of it. Some big trees. You'll start seeing some boulders here in a little bit. And I'm scared. What this flow is, it's not just a flood. Lahars have a lot of sediment in them, and the sediment makes them the consistency of. All dry. There hasn't been water down here. Look at all this. And it gives them the consistency of wet cement, and they can carry really big objects a long way. So look at this tree. This tree is probably 50 feet long, and it's just going along, just cruising along. And Then you can see some boulders down here. And here's some more trees. This is a really, really small event. This didn't happen in association with an eruption. I'm going to pause it now. This didn't happen in association with an eruption. It happened, there's glaciers on Mount Rainier, and in the summertime, they can get a lot of meltwater ponding up underneath, kind of dammed by the toe of the glacier. And then the dam can get, or the amount of water behind it can get large enough that they just rush out and flow down the slopes and pick up a lot of debris and become something like a lahar. So that just gives you a sense of the process. And for Mount Rainier, this is a big issue. This is a valley here that is built on top of lahar deposits that were carrying really huge trees. This was a lahar that came down 500 years ago, 1500 AD, that started as a collapse off of Mount Rainier. There was no eruption. It was just a landslide that caused this. And if that were to happen today, there's tens of thousands of people that are in harm's way for this particular, that particular event. So that's something that we're very concerned about and working on actively. So that's volcano research. I'm going to quickly pivot now to monitoring. This is kind of the research defines the problem, what's happened in the past and what are we going to need to be worrying about in the future and the present. Monitoring is a way of mitigating this. This is a way of giving us, giving society a chance to react before a volcano erupts and to potentially get people out of the way if that's necessary. So the idea behind volcano monitoring is that this is a slice looking at the surface of the earth and going down. So this is a volcano vent, and here's a little lava dome, and here is a blob of magma. And it's just kind of hanging out down there. But if it starts moving towards the surface, it will cause earthquakes. It needs to break a pathway, so that'll cause earthquakes. It also is going to release gases, because as it's rising upwards, there's progressively less and less amount of earth on top of it. And so that means the pressure is reducing. And what happens is it's just like what happens when you get a Coke bottle and you shake it up and then you twist the lid just a little bit and all those bubbles come out. That's because you reduce the pressure a little bit and the gas, instead of being happily just kind of floating around the liquid, comes out. And so that happens with magma as well. And those gases, when they come out, they rise up and we can measure those at the surface. And then lastly, as the location of the magma moves, or the volume, that will also push around the surface of the earth, making it move upwards or downwards or sideways. And we call that surface deformation. So we've learned from volcanoes around the world that these three types of phenomena are the most common ways that volcanoes provide us warning before they erupt. So a lot of the monitoring strategies that are out there are designed to detect these things. And so this is a cartoon that shows a number of the techniques. For earthquakes, we use seismometers. You can also use now, we use seismometers, and they're varying degrees of sophistication now. But basically they're buried in the earth and they detect vibrations that are picked up by anything, earthquakes or lahars or others. For deformation, you use GPS right now. GPS is a really important tool that's come around in the last 20 years. And that allows us to really detect precisely ground deformation on the order of, you can get down to like less than an inch with really sophisticated devices. With gases are pretty noxious when they come out of volcanoes. There can be a lot of sulfur dioxide, and that can really be a problem for people to be there, as well as for instrumentation. So a lot of the gas monitoring work is done by airborne or by ground, where you're shooting through or looking at volcanic clouds that are coming out. But we're starting to get good at designing equipment that will actually survive in this environment. And Mount St. Helens, I'll show you a picture of it in a minute, has a real-time gas monitoring station that's in this kind of a cloud, and it's actually been faring pretty well. And then there's other things we do, like we use helicopters for thermal imaging and webcams and the like. And the technology world just keeps on expanding with the number of things that can be thrown at a volcano. But these are some of the basics. This is a picture that shows a fairly typical site for us for the Cascades Volcano Observatory. This is located down in Central Oregon, near Newberry Volcano, for those of you who know know of the volcano. And what this shows, this hemisphere disc over here is the GPS antenna. It is anchored into the ground. It is going to stay there forever. And its job is to receive GPS data, just like what we all have on our phones. And then it repeatedly reports its location. And with that, we can tell if the location's changing on the order of, like I said, down to less than an inch. There's also a seismometer that's buried underground right about here. And then this is an enclosure that's about 5 by 5 by 6 foot that contains batteries, it contains electronics, it contains a radio. The batteries are powered by solar panels. And then this is a radio antenna that's beaming the data out to a place where we're receiving that information that it then gets onto the internet and comes up to CVO. These sites are engineered to be out there without us touching them for up to 5 or 6 years. And that's where the solar power comes in with the batteries. And the only thing we usually need to be able to do, hopefully need to be able to do, is to swap out the batteries about every 5 years. But this installation is fairly robust in terms of being able to withstand winter. Here's a non-standard installation. This is up about 11,000 feet on Mount Rainier. And you can see it's surrounded by glacial ice, and it's in a nasty place that gets tens of feet of snow a year. So we have to design it differently just to withstand the snow load. And that's what that looks like. One of the challenges is in the Cascades, we get lots of snow. This is a pretty critical site at Mount St. Helens that's in the crater. And every so often it gets so buried that the radio stops being able to transmit through the snow. And so then we send crews out there to dig it out. And you can see people here had a fun couple of hours excavating a snow cave. Oh, I lied. There's no gas station, but there's also a gas station at St. Helens. So where we are in terms of the monitoring in the Cascades is we're doing okay in a number of volcanoes and not so okay in other volcanoes. So Mount St. Helens is the gold standard. We've got 20 seismometers, 20 GPS stations, one gas station, and so on. Mount Hood's got 11 seismometers, 6 GPS stations. Mount Rainier, 15 and 6. But then you go to Glacier Peak, and we've got 1 seismometer. And that's been there since 2001. And we recognize that's a problem. And we started a permitting process with the Forest Service back in 2015 to expand that network by 4 stations. And that permitting process is still ongoing. It's complicated. It's in wilderness. There's questions about access with helicopters. And that is all being worked out through the process that needs to be worked through for doing any kind of work in wilderness. For what we know about what's out there at Glacier Peak, so this is not the greatest map for showing, here's Glacier Peak right here. This is the summit. This yellow triangle here is the 1 station that's operating. It's run by the University of Washington. And not a lot of earthquakes out here. That's partly because there's not a very good seismic network at all. But these yellow dots here correspond to 2 events that happened back the Wednesday before Thanksgiving in 2015. It had a magnitude 3 and magnitude 3.4. And then also a couple other earthquakes in between that. It was interesting because sometimes this is how volcanoes wake up, is they start off with 3s and 4s, and then things get interesting. So in this case, that could have happened. It didn't happen. And but this is what that looked like as far as the seismic record's concerned. This is what we call a web recorder plot. You can see these, find these on our webpage. You can find them on the webpage of our cooperators, the Pacific Northwest Seismic Network that's operated out of the University of Washington. You read these like a book. So oldest time is at the upper left-hand corner, youngest time is at the lower right, and you go left to right and top to bottom. And then each of these hatched lines is a minute mark. So you can tell time that way. And this is what that earthquake sequence looked like. Here's a magnitude 3. And then about an hour later, magnitude 3.4. And then here are a few aftershocks. There's a lot of other little earthquake-like signals on this 1 station. This is the 1 station at Glacier Peak. And these, for the most part, are glacier quakes. There's a glacier that's nearby, and it makes a lot of noise as it's popping and moving around. We only have 1 station, so we can't totally be confident that these aren't small earthquakes, but we're pretty certain that they're glacier quakes. And these earthquakes, in contrast, look a lot bigger, obviously, and a lot different. So that's what that looks like. And we haven't had anything like that happen since then at Glacier Peak. And knock on wood, it won't happen until we get a better network out there. This is where that network would be. So here's Glacier Peak. Here's this one active station. And then here are 3. This is actually one alternate, but we put one here and then one there, and that's what's in the permitting queue right now. So that's monitoring. The last part of what we do is community preparedness. And for a scientific agency, for scientists in general, this is not something that people typically think of for that about what scientists would do. In the volcano world, we learned a hard lesson. We started learning that in 1980, that it was important to be involved with people who were impacted by the eruptions and managing the eruptions. But in 1985, there was a humongous tragedy in Colombia. A volcano called Nevado del Ruiz had gotten restless a couple months into 1985. And actually some USGS folks that had been involved in Mount St. Helens came down to assist Colombian colleagues in the monitoring of the eruption or the volcano. It's an ice-clad volcano, much like the Cascades. So it had Lahar hazards. The hazards were known. And then one day it woke up and it erupted and put an ash cloud up in the air. The hot stuff came down and landed on the ice and melted it and produced a Lahar. Scientists were aware that the eruption had started, but for a variety of reasons, the word never got down to the people in the town of Armero. And 2 hours later, a large Lahar came through and killed over 20,000 people. And this is that number is a tragedy any way you cut it. But what's particularly tragic about this is that these were all preventable deaths. 2 hours is plenty of time for people in this community to move, maybe a half hour or an hour if there are mobility issues to get to high ground, which is over here. And there was plenty of time for that to happen. For a variety of reasons, the word that the scientists tried to send didn't make it down here. Either it didn't make it because the connection was broken, or people who heard it didn't believe it or didn't understand it or didn't trust the messenger. At any rate, it's now regarded as a large-scale failure on the part of the scientific community to really take the community preparedness part seriously, that we need to be involved, that we can't just hand that off to local officials and say, go for it, that we need to be involved as well. So at CVO, the ways that we have been attempting to do that is through producing products like this. This is a simplified hazard map from Mount Rainier. This has been co-produced by the Washington State Emergency Management Division and also the Washington State Geological Survey, and also in partnership with some counties here, particularly Pierce County. And this takes our simplified hazard map, puts it on a GIS layer where you can fairly clearly see locations. And then there's information about what to do should Mount Rainier erupt. And this is a product that's been put on roadside signs. It's been fairly widely distributed through public events and things like that. So this is an example of a product that we hope helps people understand better what kinds of things could happen at their volcano. In terms of clarity of communication, when we do have something to report at a volcano, we have a formal alert system that has language that's that's very close to the National Weather Service. So right now, all volcanoes in the Cascades are at normal and green. Normal is for ground-based hazards. The colors are for aviation. And then we would start marching up this color scale and this advisory scale as the volcano wakens up. And this is a system that's used by all observatories. And we try and have language that's fairly jargon-free in terms of explaining what's going on at the volcano. We also have response plans. There are working groups for all of the major Cascade volcanoes that consist of land managers, emergency managers, county officials, tribal organizations that have a stake in the response to a crisis at a particular volcano. So there's a Mount Baker Glacier Peak coordination plan that was last put together in about 2012. And these define roles and responsibilities and how we're going to start communicating if and when a volcano wakes up. And that gets us off on the right foot a lot quicker to know who to talk to. And for people who are hearing from the Cascades Volcano Observatory, they need to know who we are. And these plans help ensure that that's going to be the case. A lot of partners involved in this. A lot of the work of our observatory is to understand who those partners are and keep those relationships fresh. So there's a lot of work in the outreach department on that front. And also a lot of work being out in the community. And so a lot of presentations, a lot of working and workshops with policymakers and emergency managers, and also working on science and education. So that, in a nutshell, is the Cascades Volcano Observatory. And the last thing I want to touch on is that at the observatory, there's a wide range of specialties that are there. And that's because volcanoes are very complex systems. And so we need geologists to understand the geologic record. We need seismologists to understand earthquakes. We also need geochemists to understand gas chemistry and what different components mean. We need people who understand remote sensing. We need people to understand how to make all the equipment work out there, especially in the harsh conditions that we arrive at. We also need administrators and software specialists and GIS specialists and outreach specialists and a lot of ISTs. The point of this is that sometimes people think of volcanologists or people that work on volcanoes as doing one specific thing. It came up as like Pierce Brosnan, from those of you who've seen Dante's Peak, of having a certain skill array. But the truth is that a lot of us have grown up in specific stovepipes of chemistry or physics or math or geology or computer programming or administration. And we've come to the observatory because we're interested in volcanoes, and we all have an understanding of the language of volcanoes and how our different specialties fit into the bigger picture. So there's a lot of communication across these different specialties, but you don't have to be a geologist to work at a volcano observatory, or even a research scientist. You can be an engineer, somebody who's really, really good with your hands. So that's the last thing I wanted to leave you with. And thanks for spending part of your evening with me, and be happy to take any questions.
Great, thank you, Seth. Yeah, so there's a little bit of delay, so we'll give some time for folks to continue to ask questions. And just as a reminder, you can type questions into the comment section, and then I will ask them. Is there any understanding as to why Mount St. Helens is so active compared to all the other volcanoes?
Yeah, that's a really good question. And the general understanding of how volcanoes work is that there are time periods when they are really active and other time periods where they're not. So if you go back earlier than 4,000 years ago at Mount St. Helens, there's a gap between about 4,000 and 10,000 years where there were no eruptions. So the way that I like to think about it is that magma is coming from a deeper part in the earth and moves into a spot that's, let's say, 10 miles below the surface of a volcano of Mount St. Helens. And then that magma just kind of sits there and feeds these eruptions every so often, and keeps on doing that until that magma has shrunk down to the point where it can't do that anymore. And then it has to wait around for the next big slug of magma to come into that kind of level. And so Mount St. Helens, and using that model, it's not a great, it's not perfectly accurate, but it's a reasonable analog for what could be going on. And so right now, Mount St. Helens has something like that underneath it, miles and miles down, and that's and we'll just keep seeing eruptions until that goes away. Mount Rainier had that, say, 1,000, 2,000, 3,000 years ago. Maybe it doesn't have it today. So that's an imperfect explanation for how it could be. But what we do tend to observe around the world is that volcanoes go through phases where they're very frequently active and then not active for a long time.
Great. So last week we heard that there were some effects of the COVID-19 pandemic on studying the glaciers in the national parks of Washington. So I'm curious if there have been effects of studying the volcanoes and activity of volcanoes from COVID-19.
So also really good question. And for sure, we've been impacted like everybody else. We're all teleworking, so we don't have this environment where we've got geochemists and geologists in the same space. And that's definitely impacted things. But in terms of the baseline job of monitoring, that can be done remotely very easily. We are doing field work to support monitoring We did a very active field season this year, and we had additional restrictions to mitigate the COVID hazard. And so we have only one driver going out, and we tried to have people not stay in hotels, that kind of a thing. If we were doing helicopters, only one person in the helicopter, that kind of thing. It did impact people coming from out of state, coming up here to do particularly geologic work, and just the travel part of it from some states that had large infections going on. That was problematic. So there wasn't as much that was done. I'll say our colleagues in Alaska had a very large program plan that was using a ship. A lot of the volcanoes in Alaska are best accessed from the ocean, and they had a large multi-person crew planned for using a ship to visit a number of volcanic centers, and they had to way curtail that back and institute quarantines before and after, just to make sure that COVID didn't make its way onto the ship. So there have been some impacts, but for the bottom line job, the Cascades are as well monitored now as they would have been pre-pandemic, and we got most of our fieldwork done. Actually, the biggest impact this year was the wildfires. We had a whole solid 3 weeks where we couldn't do anything, either because of fire danger or because the smoke was just way too awful. And that was we only recovered from that because it was a late onset to winter.
Thanks. So do you have confidence in the one monitoring station on Glacier Peak if Glacier Peak were to awaken, like you say?
Well, I will say it's a great station. It's been there for a long time, and it's not needed a lot of attention in terms of monitoring. It's a University of Washington station, so lots of props to them. It's very difficult to do the job of volcano seismology with one station. It's very hard to be able to say uniquely what a particular signal is if you can only see it on one station. We do benefit from having a regional network in Washington. And so those earthquakes I showed you from 2015, the magnitude 3s and 2s, those were located, and they were located because they showed up on stations in Chelan and in Everett and in Bellingham. And so there was enough information to be able to locate them, but the precision of that location was actually not that great. The error in that, you could move the earthquake around a couple of miles in either direction and still kind of satisfy the data that was there. And so being able to move it a couple miles means you can move it either away or closer to the volcano. And in 1980 with Mount St. Helens, there was a similar situation, just one station, basically the same distance as the one station at Glacier Peak. It was just a couple miles away. And the first earthquake was a 4.1. And the rough location was understood, but there was a lot of error with that. And that error translated into uncertainty in the interpretation. And for the first couple of days, seismologists were entertaining the likelihood that it was just a tectonic earthquake because could have been located off the volcano. But instead, it turned out it was located under the volcano and off it went. But that kind of uncertainty you don't want to have in the first couple of days, because that's really your bonus time. That's the bonus time for society to react. And so our goal really is to reduce the uncertainty as much as we can by enhancing the precision of the information that we're getting from the volcano. And these 4 stations that we're proposing to add would be a huge boon to our ability to really nail down earthquake locations, and also probably we'd be detecting more earthquakes than we know about right now.
All right. Related to that, Steve has a question. What's the timeline for getting more sensors on Glacier Peak? I know you mentioned a little bit about the whole permitting system with the Forest Service, and then what's the minimum that you think Glacier Peak should have?
Right. So what's proposed for Glacier Peak is 4 new sites that would be seismometer and a GPS. And GPS is really important because when we get a swarm, the next question we want to know is the volcano deforming? And so we need both. So it would be a 5-station network when all is said and done. And that's not sort of up to standards, the standard, what we sort of aim for is, a dozen or so. And I don't know if you remember, but the monitoring map I showed for all of the Cascades had like Mount Hood at 11 and Mount Rainier at 15. And those are the kinds of numbers that we're aiming for the very high threat volcanoes. Mount Baker is another volcano that is under monitored. It's got three sensors there. And just want to introduce my dog, Tika, our dog. And so those are places where we're focused on trying to bolster it. It's also very hard to work out at those places, and so it's going to be slow going to get up to a dozen. Wilderness is real. We respect wilderness. A lot of us enjoy wilderness, and so we don't propose these things lightly. And also, it's very hard to work in places where there's old growth forest. Our sensors need to be able to see the sky. The GPS needs to not be blocked by trees. The radio antennas can't shoot through trees, and solar panels need to be able to see the sun to charge. And so there's not a lot of places where we can put the things to make them work. And we also don't want to put them like, at 10,000 feet up on Glacier Peak, because then there's other issues like, tremendously harsh weather. So getting a dozen station network out at Glacier Peak is going to be a big chore. And what we are focused on is to sort of get it up to a basic level where it would be okay. We would have some good information that would definitely be a lot better than what we have right now. It wouldn't be where we want to be, but it's a first step.
Great. All right, and then we have a question from Martin. As far as is known, do volcanoes always have hints of activity before more explosive eruption occurs? And then there's a second part to that. So you can answer that one first if you want, and then I'll ask the second part.
Okay, yeah, that'd be better than me remembering.
Yeah.
Yeah, so it's a huge question. How much warning would you get from a volcano when it wakes up? And what we hope is that it'll give us, at least a week or something like that. And that tends to be the experience, is that normally volcanoes wake up and they give you weeks or months of warning. But it really does vary. So Mount St. Helens, 1980, first earthquake was on March 20th. That was a 4.2. March 27th, first explosion. That wasn't the eruption, but that was the first explosion. So that's 7 days. Same thing happened when it woke up in 2004. First earthquakes were September 23rd, first explosion, October 1st. That was 8 days. So that's sort of 8 days to get yourself going before something comes out of the ground. Other volcanoes, there's a volcano up in Alaska, Mount Spur, 1992, over a year before it erupted, where it had elevated seismicity. On the other side of that, volcano in Alaska called Okmok, 2008, about 3 hours of warning before it had a fairly impressive eruption. And in Japan in 2014, there's a volcano called Mount Ontake that, out of the blue, had not a magmatic explosion, but what's called a phreatic or a steam blast kind of explosion. It's a volcano that people climb. It's a sacred mountain, and there were over 60 people that were killed. And then most recently, White Island volcano in New Zealand in 2019, it had a sort of surprise steam explosion that killed a number of tourists that were on the volcano. And this is a volcano that was visited daily by tourists. And so that leads me to a qualification on the answer, which is that when volcanoes are coming from, basically they're cold systems and they're waking up, that's a situation where we expect there to be days, weeks of warning. In a situation where the volcano is already warmed up, there may not be as much warning. And that's the case at New Zealand, in White Island. White Island is a volcano where you go out there and there's steam coming out and there's boiling fume rolls, and it's not uncommon for it to have small explosions. And it's monitored, and actually 3 weeks before it erupted, the New Zealand agency out there had raised the alert level on there. Not, to like evacuate, but they'd said, there's something interesting going on here, and people should be aware of that. But the explosion itself, total surprise. Nothing in the data would have told you 5 minutes before that was going to happen. And so when a volcano is restless, then things can happen very quickly without a lot of warning. And that's a real eye-opener for working close to volcanoes, and also for situations where you have volcanoes and people and infrastructure close by. One of the volcanoes that we worry about waking up is not because we think it's going to happen, but if it does happen, the problem is Mount Hood has the city of or the town of Government Camp right at its base. There are 2 major ski areas going right at the flanks, and there's 2 major transportation corridors that are also going through that sort of dark pink area, the near field area where things can happen very fast. Those would be areas that would be very problematic for people to be in because things could happen very fast without a lot of warning. And that would be a place where the situation would be extraordinarily tense and extraordinarily fraught. And for that reason, none of us want to see it wake up while we're in our lifetimes, because it would be a really, really big deal. But that it's sort of a 2-tiered answer. If the volcanoes are cold, we expect to get a fair amount of warning. If the volcanoes are warm, it could happen without a lot.
All right. Just reading his second part. I'll just read it out loud and we'll decide if you answer it. So it says, if so, is there a usual time period of awakening, or does it partially depend on how much monitoring has been put in place?
Yeah, so that it sort of continues the answer that our experience has been that when volcanoes start to wake up, the initial signals are really subtle. Small earthquakes, small amounts of deformation, maybe small amounts of anomalous gases coming out of the surface. And those are things you just don't see unless you have stations on the volcano. And in Mount St. Helens 2004, the initial part of that eruption we could see from stations far away, but in the middle part of the eruption, the only things that were tracking deformation or seeing earthquakes, because they were so teeny tiny, were in the crater. And so you really do need to be in close. And so our general philosophy and our strategy is to provide society the earliest possible warning. This is why we want to have networks that are like a dozen stations, because we need a number that are close. And that'll give us the best ability to catch the earliest warning signs and to give society the longest amount of time to respond to it. And you really want this to be a gradual curve to respond to. You don't want to be like, all of a sudden there's the magnitude 4 and you've missed a couple days before that.
Right, yeah. All right, so we have a question from Michelle, and she's wondering, if Glacier erupted during the summer months, would there be lava flows that could cause fires?
Fires, that's an interesting question. And it's not, wildfires aren't the first thing that we think about when we're thinking about hazards with volcanoes. It's certainly possible. With the blast, so Mount St. Helens 1980, that happened in, that was May 18, that was sort of in the late spring. There was still some snow out there. That eruption initiated with this incredibly powerful lateral explosion that went out for 18 miles, knocked down, a ginormous number of trees. There were forest fires that were, there were trees that were burning in the aftermath of that, because that was hot gas and ash. But that wasn't the big problem in the end. That wasn't, that didn't trigger this, maelstrom of fires like we had in early September, early and mid-September this year. And so I think, that is maybe one data point to suggest that that's probably not the thing that emergency managers need to concern themselves with the most. Another, this is actually really not relevant, but just a story, is what happened in Kilauea in 2018. Their lava flows were going through forests and neighborhoods, and they'd catch trees on fire, but there never was a huge forest fire. And part of that, and this is why it's not relevant, is that Hawaii is wet. And so, there's, the vegetation is not just like tinder dry like it is out here in August and September. And so, it's a possible scenario. And there are places in Oregon in particular where you do get more Hawaii style type lava flows. And if those were to occur in the conditions that we had this last summer in a pretty big forested area, for sure, there could be some forest fires that would be kicked up by that.
Great, thank you. And then we had a comment from Jim saying that he thought this was a very interesting program.
Oh, thanks,
Yeah.
Jim.
Yeah, and I think, a question that I have, I'm curious if, maybe this is a silly question, but I think it's fun. Do you have a favorite volcano after studying so many of them?
Yeah, that it's a hard question to answer. So Mount St. Helens 1980 was, well, it's a hard question to answer for two reasons. One is that there's a lot of interesting volcanoes out there. And Mount St. Helens, the 1980 eruption, when I was in college, that really captivated my interest and is really the reason why I kind of launched into attempted to launch into this career that I have now. And so that will always be an important eruption for me personally. But the reason why it's also a hard question to answer is that the 1980 eruption was tragic, and there are 57 people that were killed. It still is the largest disaster to happen to Washington State in terms of lives lost that we're aware of, with the Oso landslide now being number 2. So the human cost was tremendous, and I have some friends who lived in Vancouver that summer, and they describe it as the summer that wasn't, or the lost summer. And there's some psychological toll that went along with that. And for the people that were involved in the response, it was a very intense period. For people at CVO, one of our colleagues was lost. We're named the David A. Johnston Cascades Volcano Observatory after David Johnston, who was a scientist that was stationed out at the observation point, that was staffed 24/7. And had the unlucky task of being there when the landslide happened. And all he could do was get word out, say, Vancouver, Vancouver, this is it. And then the cloud got to him. So a lot of personal tragedy in that as well. And so I don't talk about favorites for that reason. But definitely there are a number of volcanoes that have had a huge influence on my understanding of the world, and also selfishly, my career.
Yeah. Well, Seth, it doesn't seem that there are any other questions, but I agree with Jim's comment of this being very interesting, and I really appreciate the way that you were communicating all of that information. I understood all of it, and I assume that means all other folks watching felt similarly. There's a lot of information, and yes, all very interesting, and I really appreciate you presenting for Wenatchee River Institute and our community.
You bet. Yeah. And thanks everybody for taking some time tonight.
Yeah. Have a good rest of your evening.
Thanks. You too.